And this class is for the Ehrenfest theorem. So let's see the statement of the Ehrenfest theorem. So it states that the Schrodinger wave equation leads to the satisfaction of Newton's law of motion on the average. So the average motion of a wave package agrees with the motion of the corresponding classical particles. So Ehrenfest theorem is more or less like the Newton laws of motion in the classical theory, in the classical physics. Okay, now let us try to see the proof of the Ehrenfest theorem. Now, the average expectation value of position r of a particle represented by psi is this one. We have already done this, equation 1. Now, if we want to find out the average value of velocity of a particle, we just need to differentiate position with respect to time. So this will give us the velocity. So in that case, the whole term will be differentiated with respect to time. Then we are going to get this one. If we differentiate this term with respect to time, so we're having two terms. One term is your psi star, another term is your r and psi. So in that case, we are going to have two terms here. Okay, it's applying the differential for multiplication. Right? Now we'll get equation 2. Now we already know the Schrodinger equation. Schrodinger equation is given by this one. Alright, when you have an external field, external force. Now, if we take the complex conjugate of Schrodinger equation, if we take the complex conjugate of equation 3, then we're going to get equation 4. I will be replaced by minus I, psi by psi star, and here psi by psi star, and here also psi by psi star. So this is your Schrodinger equation, and this is a complex conjugate of your Schrodinger equation. So we can rewrite equation 3, okay, in this way, which means IH will go on the other side, and you will be left with psi star del psi of del d. And similarly, we can arrange equation 4 in this way, and which will give you your equation 6. So we are getting equation 5 from 3 and equation 6 from 4 by rearranging equation 3 and 4. Okay. Now, if we substitute equation 5 and 6 in 2, so we know that this is your equation. Alright, for your velocity, this is your equation. So in equation 2, if we put the value of del psi star del d, del psi del d, then we will get this one. And here, you should put a bracket here. So this r psi, it belongs to the holding, alright? It belongs to the holding, alright? And now, if we further simplify this one, we are going to get here IH2M, and this is the result that we are going to get from here. So if you don't understand how you are getting this term from the above, you can please comment in the comment section so that I can make a short video of how you are getting this term from the above equation. Okay, so here we are having two terms of integration. This is one term of integration, and this is your another integration. Okay, so we will keep equation 7 as it is, and we will further try to simplify the integration, and at the end we will come back to equation 7. So we will consider only the second part of the integration. So the second part of the integration is this one, and this we can write this integration in this way. So you may be wondering how you are getting this two term from this term. That is your equation 8. Then this is your note. So this note will help you to understand how you are getting equation 8. So see, we are taking this term, that is this one, and we are considering r psi as x and del psi star as y. So if you differentiate x, y, it should be x dy plus y dx. So what is your x? That is your r psi. What is your y? That is your del psi star. So if we put the value of x and y in this equation, then we are going to get this one. And this is exactly your equation 8 without integration. So we just need to put integration here. So that's how we are getting this two term from this term. Alright. Now, what happened here if we apply the Quotient divergence theorem? So here it should be del This is a divergence. Okay, so here if we apply Gauss divergence theorem, so it can be replaced by this one. Instead of having volume integration, it can be replaced by the surface integration. But we know that this term will be, this term represents the normal component of a vector since psi tends to 0 as r tends to plus minus infinity. Then in that case, this term will become 0. So in equation 8, this term will become 0. So you are left only with this term. So equation 8 will reduce to this one. So one term on the right hand side is already 0. So only one term is left. Again, this term you can also write in this way. Similarly, alright, like we have done in the note. In the same way, even this term you can write in this two term. Alright, so what happens is that again, this term as a divergence of the whole function, by applying the Gauss divergence theorem, this term will also vanish, that is, it will become 0. So you will left only with this term. So your equation 8 will further reduce into this equation. This is our simplification. So this is your equation 8. So equation 8 has further reduced into this equation. Now we need to replace this del square r psi. So here we are having here psi star del square r psi. So instead of here del square r psi, we'll replace this term with this two term. So how are we getting this two term from this one term? So it is being given in the notes. So here this is your del square r psi, del square r psi. So here also we are considering r as x and psi as y, and we are simplifying it. So what happens is that we are getting this term. Okay, this is our simple simplification. I think you guys will be able to do it. And what happens is that after getting this equation, we'll try to substitute the value. Our x is nothing but r, so we'll put instead of x, r, and our y is nothing but psi, so instead of y, we'll put here psi. So you need to change here. Instead of y, you should write psi here. It's equal to 2 t of del x represented by the operator del, and y is nothing but your psi, x is your r, del square, so it's second order derivative, so it will be replaced by del square, y, so it should be replaced by psi. So if we see that, then this is nothing but your this two term in equation 13, so which comes directly from this term. All right, so now finally you have equation 13. So when we put equation 13, as I said, in equation 7, so we are coming back to equation 7 after solving this integration. Okay, so if we put a value of this integration in equation 7, then we are going to get this term. All right, IH2m, this term, the first term will stay as it is, but the second term we are going to put the value. So after further simplification, if we multiply this psi star to this two term, then we are going to get this one, and this two term will get cancelled, this two term will get cancelled, and we are left with only this term. And if we further simplify here, we are going to get this one, but minus IH del, it is nothing but your momentum operator. So this can be replaced by the momentum operator, this one. So you are getting d r of dt. So if you differentiate position with respect to time, so this is your velocity, you're going to get here, this is nothing but your expectation of momentum divided by the mass. This is your equation 14. Now if we differentiate the momentum with respect to time, then we are going to get this term. So this is your external force. Okay, now but this term is the average value of force acting on a particle moving in potential field V. So according to Newton's second law, it says that force is directly proportional to the rate of change of momentum. So this is your Newton's second law of motion. And here equation 15. Now equation 15 becomes d of dt b is equal to minus this equation. So instead of this term, we are going to put the value of force. So here this is your expectation value of force. Again, here where this term should not be there, simply expectation of P is equal to m d of dt. These are simple simplification. So here equation 16, this is your equation 16. Force is equal to dp of dt. So which is the second law of Newton's second law of motion. So equation 16 represents the Newton's second law of motion. This proves Ehrenfest theorem. So generally, your momentum expectation value of momentum is equal to mass and d r of dt, because we know that momentum is given by mass into velocity. So this is your mass and this is your velocity. Okay, and here also force is nothing but the rate of change of momentum. So equation 17. So equation 17, called the Ehrenfest theorem, are the quantum equivalent of the equation of motion of a classical particle.